Okay, so what we're going to do now is just cover the efficiency equations for both the solar air thermal and the solar water thermal systems. And what we're going to see on both, the math is exactly the same. The only thing that's going to be different is the density of the fluids moving through the two systems. So they're both solar thermal fluid systems. In one case, the fluid just so happens to be a gaseous fluid, i.e. atmospheric air, and in the other case, the fluid happens to be water, right? And so there's innumerable fluids, right? We could have compressed natural gas through there, we could have ammonia, we could have some kind of weird refrigerant, but we're just using the fluids that are most readily available in nature, air, water. So they're both. And I'll just go ahead and write that out.
They're both considered fluids?
Yeah. Solar. Right. Solar thermal fluid systems, and that's something that comes out of engineering, where the word fluid actually has a specific meaning. It's a fluid as opposed to a solid. And if you were to draw a Venn diagram, you could do it like this and say, okay, here are all fluids, and over here you could say, okay, these are all gases, and over here these are all liquids. And I don't think there's anything outside of that Venn diagram, but but within gases you could have air, you could have steam, etc. Here you could have water, oil, but they're all called fluids. So that's a specific language. Okay. So what we're after here, in fact the initial name of this project that I called it was energy efficiency. And I call it energy efficiency for energy independence, because in my opinion, and I think a lot of people's opinions, we just waste a lot of energy. you look at our gas mileages, you look at our poor insulation, you look at the fact that people are still throwing food away, things of that. And so I'm like, why are we so wasteful? Well, the opposite of waste, my opinion, is efficiency. So big picture here, let's just look at a house, and we'll look at a house in the winter, and the sun still shines in the winter unless there's clouds, obviously. And the problem with the sun being here in the winter and the house being let's just say warm, but too cold, and the outside just being basically too cold, is that what's going on? If you have a warm body here for the house, cold body out here, what's happening? What's happening between that warm house and the cold air outside? What's going on? Yeah, and it's going to be heat transfer via what three modes? Well, the three modes, you've got radiation going on. I'm just going to draw it like this. Radiation. So anytime two bodies are at different temperatures, radiation is occurring. You're also going to have convection.
Isn't radiation and convection the same form?
Radiation and convection are not the same. Radiation is transferred with photons. Light, ultraviolet, infrared, etc. Convection is transferred with mass. Actual hot air molecules moving away. And the third one is conduction. And conduction is more or less, think of bumper-to-bumper traffic. Like if one car in the back bumps another one, it's going to bump the car in front of it, car in front of it, car in front of it, et cetera. None of the cars really move that far, but they transferred their energy through vibration. So the masses themselves didn't move, they just vibrated each other. So those are the three fundamental modes. And yeah, you're right. If it's warm in the house and way colder than you want it to be outside, what's your solution? Well, the sun's right up here, cranking away at our approximately 1,000 watts per square meter. With your gadget, are you able to measure the insulation? Are you able to get numbers on that? Okay, so you'll be able to plug these data, the actual data, right into your.
We didn't actually start doing it with every one until today.
Yeah, but I think you'll probably see a trend though. What it is at 9 o'clock, 10 o'clock, et cetera. So that.
Every time the clouds would come over, we'd measure the insulation.
Oh, nice.
And
That's good. So
it would drop down to like 250.
Okay, wow, 20. Okay, good. So that's really good information to have. Just showing that fluctuation as a function of cloud cover, time of day, et cetera. Perfect. So, but we know, so all the energy that we get from the sun, it's not convecting or conducting energy to us. It's all coming from radiation. Okay, so here comes the efficiency part. Well, if this radiation is hitting the house, and I'm just going to draw let's draw a nice little sun ray coming in. It hits the house, it bounces off. That's a wasted resource. It's a wasted potential resource that you could have used to heat the house. And that's exactly what you're doing with your two technologies. So if I just take this whole thing, all copy, paste. So what we're going to do to fix that is come in here and build your solar collector. And so the radiation, rather than bouncing off, is going to go into your collector. And I think we all know already that let's go back to our efficiency equation, equals power out over power in. And I think you guys are fairly clear on what the power in is. It's just going to be, and I've been using the letter phi for the solar constant. So phi equals 1,000 watts per square meter. You've been measuring it exactly, but that's your power in. You're going to multiply that by the area of the collector, and you're also going to take your sine theta. Now, and this gets back to those two Euler angles before, because you actually have two angles. You've got your elevation angle and your azimuth angle, but at the end of the day, you're going to want to combine those into a single angle that's going to be between 0 and 90. And we'll figure out the formula for doing so. And so that's sine theta. And it's going to be more complicated if you have both angles going on. And again, sine theta is, it's this angle right here. Well, it's the angle that the sun's rays make with the panel. It's not the azimuth, it's not the elevation, it's the combination of those two. We can take a look for that. Okay. So what we're after here, this is I think you're pretty clear on the power in. What we need to get after next is the power out. And Serenity, you made a really good shot at it. You were super close to getting that. So let's just review kind of big picture power issues. So in I'm just going to write this down. So in a mechanical system, so power for mechanical linear. Anybody know what the formula for linear power is in a power system? So if I want to know the power in a car, how I would calculate that?
Joules per second watts.
Well, yeah, it's going to be measured in watts, but what two things about a car could I measure to get the power?
Weight, mass, and
Velocity.
Velocity is going to be one. I'm going to put velocity right here as a little v. The other one is the force. So the force between the tires and the road pushing you down the street. So that's linear mechanical energy. Now, or power. So now if we do power, mechanical, rotational, there's one right there. There's the wind turbine behind you. We're building a water micro hydro wheel. So same thing, it's still a mechanical thing, but now we're rotating. In that case, we're looking at the torque, so how hard it's being twisted, times the angular velocity. It looks very similar to the linear, right? So you're just replacing force with torque, and you're replacing velocity with radians per second. Let's do a really easy one here now. So let's do power electrical. I know you guys all know that one, right? Which electrical variable is analogous to force? It's voltage. It's exactly right. Why is it voltage?
It's like pressure in the.
Yeah, it's a lot like pressure. Yeah, right. And it's between 2 points, and it's actually across 2 points. It's between the anode and the cathode. And what's the other variable?
Current.
Current. There you go. And you can see, and I'm going to write as a little kind of scripted looking eye there. And so you can see that in the case of the car, the velocity is the car moving through space. The angular velocity is the turbine blade spinning around through space. And in the case of the current, it's the same thing. It's the electrons flowing through the wire. Okay, so now let's do power, and I'm just going to call this thermal fluid. Power thermal fluid. I might have to go and cheat on my notes a little bit, but well, before I do that, I want to just, before we get to the exact equation, let's just go back here and verify with force and velocity that we're dealing with units of power. So force is going to be mass times acceleration, so that's mass times length over time squared. Velocity is length per time, and that's going to give us mass times length squared over time cubed. So those are the dimensions of power. Mass times length squared over time cubed. For the rotational, as it turns out, torque actually has the same dimensions as energy, and that's mass times length squared over time squared. Angular velocity is just measured in hertz, so that's 1 over time. And again, we're going to get mass length squared over time cubed. Okay, so what we just did was a little thing called dimensional analysis. We analyzed the dimensions of the thing. We started with the dimensions of force, dimensions of velocity, dimensions of torque, dimensions of angular velocity, and came up and said, okay, we're all on the same page. Power always has the same dimensions, just like energy always has the same dimensions. It's a little different in volts and current. There's a way to dig back into the SI units, but that's a conversation for another day. So here in our power for thermal fluid, I know that part of what's driving the power through there is going to be how much mass is flowing through the thing. So right off the bat, I'm going to write m dot. And m dot, and since I know that's my through variable, that's what's flowing through the system, is hot fluid, I'm going to write that out like so. Mass per unit time. That little dot just means rate of change with respect to time. Okay, so mass with respect to time. Now, I can see with my units up here, I need something that's going to be length squared over over time squared, right? Because if I multiply length squared by time squared times mass divided by time, I will come back to mass times length squared over time cubed. I will get that. The question now is, how do I get that out of my my system? I'm going to take a quick break because I don't know the answers off the top of my head, but let's think about that, and then we'll nail it. Cut to commercial break.